this time. Okay, so I'm recording. Audio is good. Okay. So then, as a reminder, this Thursday, we'll go over a few additional term project topics. Also, you have, for the TCP/IP attacks, you have TCP/IP attacks part 2. That's due March 4th on Thursday. This is the TCP session hijacking. Remember, we've already talked about it. You can just read through the description there, complete the TCP session hijacking problems. As discussed in class, basically send a command such as ls or pwd, steal information from the secret file in the server, and also create a reverse shell and control server from the client. Make sure you're reading through the chapters in the book also that correspond to these labs. So you have one homework assignment due Thursday. Plus, you have the Snort IDS homework. I'm going to create the link for that. New assignment. That's a short one. It's not, I don't anticipate that homework being very difficult. So we're going to say intrusion detection homework. And that's going to be due on the 11th, right? So it's going to be due on the 11th by 10 p.m. You can ask any questions that you have about it. It'll stay open until the 13th. Complete. Be attached. Network in Snort Lab. As discussed in lecture. And basically you have five problems to complete, which relate to the families of attacks, right? So if you remember, it's, what are they? It's scanning, was that the first one? Scanning. Then it was, I think it was exploit. Oh, no, sorry. It's the first family is, so problem 1, let's say, is DDoS. Right, problem 2 is exploits, I remember that. Problem 3 is scanning. And then problem 4, find another family of attacks. And the same, so I'll say P4 and 5, find another 2 families of attacks. Okay, so that's basically what you have to do, just like we discussed in class. So you'll need to find, if you did, you launched alerts for denial of service and you launched alert for exploits and for scanning. Now you'll need to find 2 other types of families within the database of Snort in the alerts, and then just kind of repeat what you did with problem 1, 2, and 3, but for these types of attacks. So I leave that to you. Are there any questions about this assignment or the due date? Doesn't sound like there's any questions, so I'm going to save it. Okay, so seems pretty clear. All right, so that's your homework assignment that you can work on that one as well on Thursday. Now, however, there's always some students that have finished their assignment, so we have a new set of labs, right? So we have firewalls, and these, as I said, these are fun, okay? But they are involved, so they have a lot of, right, so somebody's asking me, I just opened the Snort Lab and it is blank slides. It's not blank slides. It's blank slides when you open it in Brightspace, but if you download it and open it on your computer, it'll have the data. I don't know why that's the case in Brightspace, but I always have that issue too. Just download it. It should be there. Okay? So again, I'll repeat, you just download that slides and it will show the information. And everything, as I said, I wrote down everything that you need pretty much. Any other questions?
But the slides just 3 problems.
Huh?
But the slides just 3 problems, not 5 problems.
There are 5 problems there. Okay, so let me go over. So this is the so you guys are seeing it, right? So this is the document. Click on it. You have to download it. And I do slideshow. You can see here, right? That's the Snort IDS. So this is basically the scenario. 3 attacks, problem 1. This is how you get to the signatures.
Professor, I don't see any slides.
You don't see the slides?
Yes.
I'm not sharing. Oh, I'm sorry. Yeah, okay. I'm sharing now, correct? Yeah. Okay. So you guys can see it now. Sorry. So as I was saying, I opened the slides. Basically, this is what we had covered before. This is just the classic example I always use. You know, internal network, switch 1, firewall, switch 2, DMZ, router, switch 3, the internet. So this is just a placement of Snort as you could think about it, right? Obviously, you're going to put that in your own VMware environment. SCAPI runs from the attacker, as I said, the spoofs. And then you have the Snort service running on a VM. So I showed you already how to install all of this. So basically, here is the idea. You navigate and you find etc snort rules. This will give you a whole bunch of files with an extension of .rules that have the alerts. Okay, so I'll talk a little bit more about this in the slides today, but the first problem is these 3 families of attacks, right? This is a denial of service. Remember, Snort is signature based. We talked about that as well. Here's all the code, nothing different from what we've done so far in the semester. These are actually a lot easier, right? Basically, there's the packet. The fields have to be exact because it's a signature based, and then you send out the packet. There it is. This is how you starting Snort in monitoring mode. So this is going to be a terminal on the server, and this is a terminal on the client, or the attacker, I should say. And basically, when you receive an alert, this will trigger. So this is the example of just 1. Okay. Now I provided already, what's important here is the signature. So I provided the packets for the 3 DDoS. So these are DDoS rules. You literally just have to do this. Then problem number 2 is mtalkd and mountd overflow. So if you remember your ITS 450 or other classes 250, you know about exploits. Basically the type of buffer overflow vulnerabilities, right? You usually inject some hexadecimal code and then you hope to get a shell or something along those lines. So exploit.rules, this is problem 2. Again, obviously you just have to use this code, but you change the packet because you're going to be spoofing a new type of a packet. That's problem 2. Problem 3 is the scan rules, CyberCop and Amanda. I just picked 2. And then again, you just trigger these alerts on the terminal. That's literally all you have to do. Where you're running Snort, that terminal is waiting there, and then boom, you get the alert. Okay. And then that's the lab. So you trigger alerts for 5 families of attacks. DDoS, exploits, and scans I've basically given to you. But I want you to figure out 4 and 5. So I want you to go in and find other ones. So not DDoS, not exploits, not scans, different kinds of attacks. Some of them will be pretty difficult to implement, others will be pretty easy. So I leave it to you to solve, okay? Does this make sense, guys?
Okay, so can I to just use some attacks from the sniffer or sniffing in this lab?
Say that again. So you said there were only 3. Is this what you meant, that these 2 had question marks?
Yes, which mean is we should find another attacks in this lab to.
That's right. Find other families. Don't just like find another DDoS attack, but try to explore other options, okay? There's more families than just DDoS. There's like, I think there's like 30 files in there. DDoS is DDoS1, DDoS.rules, exploits.rules, scans.rules. That's 3 of about 30, okay? So you can look for other ones.
Oh, okay.
Does that make sense?
Yes.
Okay. Any other questions, guys? I mean, this is, I mean, there's nothing else to do, right? So you just have to use the Tcpip code on the attacker and then just run this command on the, or a variation of this. You know, this is just a Unix generic command, but this is, you know, launch snort and have it monitor. Okay, so I'm not hearing any questions, so I'm assuming this is all clear. All right, so then let's go back to Brightspace over here. All right, so I've already specified that this is going to be due a week from Thursday, the IDS, and then this one sequence is hijacking, session hijacking. That is due this Thursday, and I've already seen some, some completed assignments, so pretty good. If you have any questions on Thursday, I'll have open lab. You can just ask any questions that you like. But the new lab will be this one, Firewall. You can see I've loaded 3 versions of it. You'll have to read all 3 documents, but we pretty much do everything in this lab. They're pretty much the same, so we'll do all of it. That's why it takes a while. There's a lot of topics, but it's very interesting. I think it's actually the nicest lab of all of these, and it is certainly the central topic this semester. Okay, so that is the new lab, but I'm not going to get to that right away. There's a few slides I want to go over, just a few little things here and there. And then once I finish those, I will come back around to firewalls, okay? We'll spend, I think, about 3 weeks, so certainly even after spring break, we'll still be working on this lab. What I'll probably do is I'll do every problem in there as a separate submission, given that they're kind of involved. They're pretty extensive. All right. So let's now go ahead and, and then as I said, remember on Thursday, I will also make a little bit of time for more term project topics. So there's a few other things that I want to point out that you guys could also do, all within the context of sniffing and spoofing in a network, right? So you still would need to attack and defend, but I'll just show you a few other options that you can, if you're brave, that you can try out. All right, so let's go ahead now and take a look at the slides for today.
Hey, Professor.
Hold on. Yes.
Just before we continue, really quick, because I'm asking this because it's not stated in the thing you wrote. So again, there's the 5 problems.
Going back to the lab.
Yeah, just to quickly cover one thing. So you wrote the 5 problems, P1 through P5.
Okay.
What?
P just open. Is this the one you're asking about?
Yes.
Okay, let me open it. Because I need to share this.
So I'll keep it short, just to mention.
Which one?
So You're talking about us creating the alert, correct? Pretty much alerting an attack. Is that correct?
Snort program is an IDS, okay? So
Okay.
Snort is an intrusion, just like you know what a firewall is. Well, you know, and what it does. Snort is a IDS instead of a firewall. So this is an IDS. You don't have to write the code for the IDS. You just install Snort.
Okay.
That's it.
The question I want to ask is, how do we know when we've accomplished the task per each? What are you looking for?
Yeah, so you're going to run, and you'll see this in the slides in a second. You will run, this is the command for starting the IDS, right? On the machine that, let's say, you know, you have the same thing, right? So you have a client, a server, and then in this case, you have the IDS itself in promiscuous mode. So then you turn it on, and it's going to be a terminal like that. It's just waiting there. Nothing should happen. Then you run this code on the attack on an attacker. So maybe you would have another computer or just, you know, simulate one. So you would, you know, attacker. And when attacker sends out a packet, it'll be one of these packets, remember? Because Snort is a signature-based intrusion detection system. So when this packet goes out, it doesn't matter where it goes. You know, VMware is like a hub environment, so everyone gets all the packets. So this packet will be sniffed by the IDS, Snort in this case.
Okay.
If you did everything correct, what's going to happen is on the terminal, you will see something that says alert, and then it's going to say the name of this attack. So for instance, this is, let's say, TFN, right? TFN. That's why you need to look at the DDoS.rules file to figure out, okay, that packet is for this one, TFN. You see that? And so in the little terminal, it'll say alert TFN detected or something like that. You see that?
Yeah.
It triggers an alert. That's literally all that happens. So every single attack, so in your, you need to generate an alert for TFN, TFN2, and TRIN00, right? And those are basically these three packets.
The first three. Okay.
Then you repeat it for problem 2, NTalkD and MountD. That's why I wrote their names. So when you run these packets with the SCAPI code, it'll say alert NTalkD detected, MountD detected. If it doesn't say that, they weren't detected, so you did not, you know, you did not succeed. That's the whole point. You see that?
Okay.
And that's it. You repeat the same for problem 3, and then you're going to find just two more families, and then do the same thing.
Okay.
Does that answer your question?
Yeah, that overall does.
Great. And we'll see this in a second in the slides. Anything else, guys? All right. Doesn't sound like there's any further questions. So let's move on then, again, as I said, to the slides. Let's actually then, since we were talking about Snort, let's start with those slides, I guess. So these slides are already on your Brightspace environment, so you can read through them. Link. All right, so it should be NIDS. All right, so these are the slides. All right, here we go. So we started these. I believe we got as far as half of them last week. And then this is the part that I didn't get to last week. So I kind of went over just what, you know, make sure you look at that video again, because there's a lot of valuable information there. So certainly please take a look at it. Now this set of slides is just a little bit more specific to the Snort application itself, which, as I said, it's so that you don't have to code the intrusion detection system. We can just use this Linux tool. So some highlights about Snort, so we can take a look at that. It has been around since 1998. So as you can see, it's been around for 23 years or so. It's basically, back then it was basically just a sniffer, just like your C code with PCAP or Sniffx or memcopy or the SCAPI, right? So it was a sniffer and it had no rules. Then over time, they started making releases of it and they started adding modules to it, right? So basic rules language was created of how they structure the rules. And then, of course, the database of rules themselves. It's got roughly, you can see, you can actually count. You could run a little, a Linux command there and maybe count how many rules are in all those files. But I can't remember exactly. There's about 30 files, I think. And each file represents a family of alerts, basically. So it's got more than 3,000 rules, certainly, for signature-based intrusion detection. The design criteria of Snort is a lightweight intrusion detection tool. It's cross-platform. Obviously, there's a lot of tools out there that cost money, right? This one, of course, it's available for free for us in Linux, so it provides a very good environment to understand the concept. But, it's just a sniffer with rules at the end of the day. And then what do you do with the alerts? So it's got a small footprint. It's easy installation. It's just a sudo apt-get install. The configuration is pretty straightforward on the text, text-based. It's a simple language for the rules. We'll take a look at that today. I mean, there's no real, I'm not going to ask you to create rules or anything like that. We're kind of just reverse engineering it, right? We want to trigger the alerts, and that way that gives us some intuition because you'll be creating the packets. You have to do it from scratch, right? So I didn't want to give you like the code and then you just run it. What would be the point of that? It's high efficiency, okay? And low memory and CPU consumption. That is, of course, we've talked about this quite a few times. In network security, you can't slow the network, right? So that, that it's not going to work. And so things have to be efficient. So this is, most likely built with PCAP or libpcap, right? Which is the classic library that's in C++. So you guys have a great library there if you ever want to build your own solutions. It is a packet level detection with no support for TCP stream reassembly in early versions. Okay, so mainly it is a, as you think about intrusion detection systems or firewalls, etc., you would think, well, wouldn't it make sense that we don't just look at one packet, that we should look at more packets? And that's true, right? So that's certainly a problem that's out there, which is called TCP stream reassembly. When you have a session of packets and you want to look at the whole thing, but we're just focusing on a packet level approach. It's an open source alternative to expensive commercial IDS. So I showed you Blue Vector, just the server. I think the last time I checked was $200,000, and that does not include the license, right? Which is you have to pay every month. So anyway, this this is open source, has been studied quite extensively. If you like this topic, there's a lot of books out there. Snort Bro, you can take a look at them. They'll certainly give you more intuition. Snort architecture, you can think of the network here, and then you have some packets coming in, right? So what do you have? You have the sniffer part, just that regular code that we are now very familiar with. And then Snort has a pipeline, right? So it has a pipeline that after the sniffer, it consists of the preprocessor, the detection engine, which is just, like if statements. There's obviously the rules set, which is always kind of a database that's downloadable and updatable. And then there's, on top of that, there's the alerts and logging, right? Which is, you know, the detection engine generates alerts, has logging capabilities, but then there should be a management of the alerts as well, right? So, and then it can communicate with separate servers, you know, where you can store the logs or the databases themselves. Keep in mind, you can always make, you know, unfortunately this semester we were not able to see how we can make like a Raspberry Pi. You know, we can configure it with 2 network cards and then make it into a router, and that basically allows us to create any kind of device that we want. But, you know, think of, as you're building your own experimental environment, it is possible to take a Raspberry Pi. They come with 1 network card, but it's very straight. They have a USB port, actually, that can be converted from USB to network. And so what happens there is that now you end up basically with 2 network cards. And whenever you have that, because it's Linux, basically, you can do forwarding, right? And whenever you can do forwarding of packets from one network, from one interface to another interface, you basically have a router. And then after that, you know, we can implement all kinds of tools like Snort, et cetera, and then you have an IDS. Or in this case, an intrusion prevention system, an IPS. So you have all of that flexibility, but ultimately it's architecture. It's a packet sniffer, right? It interacts directly with the network card. Obviously, you have to get the permissions there using the libpcap, library that we've already experimented with at the very beginning of the semester. As you can see in the pipeline of the IDS, there's the pre-processing component, the detection, and the alerts component, okay? And those can be thought of as plugins, right? So you can probably replace them, etc. And then also there are actually various front ends for logging, for database management, GUI, meta IDS, and so on, right? So you can see how you can build on top of this. If you can send this information to a database, then you can, you know, retrieve the data efficiently from it. The Snort Sniffer, so how it works, it operates in promiscuous mode, as you can see. It looks at all the traffic to the OS. It can perform some basic packet filtering, and it can decode the packet headers just like any sniffer would do, right? So this, if you notice, very similar C code to what you read in at the very beginning of the semester for SnifX, etc. So we're not going to get into this details. You know, we're not going to look at how Snort is written, but just, you know, it's written in C++. So you can think of the preprocessors as, you know, obviously packets might have various kinds of information, right? So preprocessors are also the idea of plugins that, you know, can look at, for instance, if there's special encoding like HTTP encoding. This should say HTTP. So HTTP encoding, you know, that's a common thing. So they might, basically, it's a way of cleaning the data. So the preprocessor, it's to clean the data. Which data? The data in the packets themselves, okay? Which is really the input to our device. Then it's got the detection engine, which is based on rules. And that's really kind of the most important thing of these slides that we're going to cover today. So that engine, basically, and the language that it uses. So the rules that you have in the files are parsed into internal data structures, as you might imagine. And then basically you have a matching mechanism. So rule matching is prioritized according to matching complexity. So it's going to look at IP header rules, TCP header rules, application protocol header rules, and content rules. I think I saw the statistic that about 50% of all signatures, at least more than 50%, was content-based. What is content-based? It just means that the payload, right? So if you remember, whenever you build a packet in Scapy, for instance, you have an IP header with some fields, concatenate it with, let's say, you know, TCP with some fields, and then concatenate it with the raw data, the raw data, etc., with some, some fields as well, some information. So this is basically the same approach. And so it does the matching based on the contents of these headers, okay? Just like you've seen me, I wrote in the lab document for you to follow. Multiple matches are possible, and then the highest priority alert is reported. So obviously there is a priority given in the alert language, so that you can, because otherwise you would have too many alerts, right? And that's wouldn't be that useful. So the detection engine is basically heuristic or if statements. So what that means is you have some packets coming in, you have the detection engine which compares two rules, right? Looks at the rules in an efficient way. We're going to learn later on that firewalls use like chains, etc., as an efficient way of checking for rules. So here you can see, do the packets match? If it doesn't match, this assumes, remember, it's an IDS. So in an IDS, the packet has already gotten to its destination. You're just mirroring a port and looking at the traffic again. So if it doesn't match, you just discard it, get rid of it. If it does match, though, you generate either an alert, login, or a combination of both, okay? So that's the general, and then this information, as in your lab, will appear on the terminal, but this could go in various other ways into a file, and then that file could be emailed, however you want to do it. Redirected somewhere else, etc. So here's an example of a snort rule. I'm sure if you've already started looking, let's say at ddos.rules, right? So if you looked at this file, you've started to see things that look like this, right? So you saw, they start with a word like alert, indicate the protocol, and then these are IPs, and then these are port numbers, okay? So there you can have either specific IPs and port numbers. You can have variables like this one and this one, which basically are, might represent ranges of IPs, several IPs, etc. Or it can be keywords like any, which just basically is like saying any, right? So any port. Then you can have flags, right? Flags that are associated with a packet, and also it's usually the message indicates the type of attack. So it's usually the name of the attack. So TFN 0, TFN 2K, or in this case the SYN, FIN, SCAN, etc. Right? So this is the thing that tells you what attack it is, because remember that all of these are signature based. Therefore, the names of the attacks are known. Somebody, basically named them. Okay, so that's the idea there. So now let's take a more detailed view of the rules themselves. They're usually a single line, right? The rules are created by the known intrusion signatures. So remember, we've talked about this. Researchers spent, 3 months looking at an attack, and then ultimately they came up with a signature for it, okay? The rules can be divided into the rule header and then the rule options. And then you can see the rule header is made up of the action, the protocol, the address, port, direction, and then the other address and port. So it's like source address, source port, destination address, destination port. And then also the direction, is the packet going in that direction, both directions, or that direction, the opposite. So you can see the example here. If we look just at the header, the yellow part, you can see the yellow part, I'm assuming. So the action here is not to alert, but just to log. This is only for protocol TCP packets. Then you can see the source IP. You can specify a subnet. Then we have the source port. We have the direction here. So it's packets going from this IP to that IP. Then we have again here the destination IP, and the destination port is just not shown, but it would be, you know, around there. Okay, so that's the rules pretty much, pretty you know, pretty straightforward really. And then over here in the options section, you might have the option keyword. So this is an example. You can see we have outside finger attempt. So option arguments, it indicates kind of the name of the attack. And then these can be separated by semicolon. So you can have more information in there. So this is called an options separator. Okay? And so this is what you will, as I said, you will be reading this. So you don't have to create new alerts, but you will have to create. I've actually had students that were clever enough that they said, I'm going to create an alert, and then I'm going to trigger it with, you know, with my packet. So, and I accepted that as one family of attacks. So if you're, you know, if you have that curiosity, you know, that's perfectly fine. That, you know, you can do that. All right. So here again, you know, another description of this. So the rules example, alert basically will be generated if criteria is met, right? Apply to all IP packets. So this one, you know, all, you know, every packet basically, and then any, right? For source IP, source port, the direction, and then any destination. And this is yet another IP packet detector, right? So this one, don't do this. Don't do this one because it's too easy. But that's an example of an alert. This is another example here of what they actually, a more complicated one, as you see it in the files, right? The .rules file. So here it's an alert TCP telnet server. So that's a variable, and it would have associated IPs for 23. Right, for telnet, the direction is important. External any, right? That's the main header, and then you have the. This is the message. So this is a telnet attempted SU from wrong group, right? This is, you know, you can create your own, as I said, and then you have a few parameters like flow from server established, right? You can see that some of the flags, the content, which is usually the payload. It means that this one, 2SU root, that's what it carries. Another semicolon for the separation. And then you know, a few other parameters, SID, revision, and so on. So a lot of these things just get into the specifics of the signature, right? So that this is a signature. So obviously, if you want to trigger this signature, you have to create the packet that has all of these parameters because it has to be an exact match. Okay, so that's just some examples of how it works. The detection engine order to scan the rules. Snort does not evaluate the rules in the order that they appear in the Snort rules file. In default, the order is, you know, alert rules first, then pass rules, then log rules. Okay. So, because, you know, that way you can mix them up, I guess. So it doesn't look at the order in the files. It just follows. I guess alerts are, you know, more important than, you know, log is. You're going to look at it later. So I guess that's the logic. The headers, so we can talk a little bit about the header. The general format is action, protocol, source address, source port, direction, destination address, destination port. Okay? An example is alert TCP bad any, direction good any. Okay? And the options are alert, pass, or log. The protocols, as obviously you know this, TCP, UDP, ICMP, and IP. The directions can be bidirectional or unidirectional. And then the variables, you know, can be basically variables, wildcards, and expressions. Okay, so you can see that there, any for a variable such as home that you need to define. The general format is key value. key value pair for the option. This is for the options section of the rules. Some example, they're separated by semicolon, you can see, and then this is a SYN/FIN scan, so it's got to have S and F flags, basically. This is very similar to how Scapy works too. So as you can see, a lot of these things, because they all pretty much use the same library, libpcap. That's one of the great advantages of this, is that they all kind of have a similar feel to it. Basic options, content. You could have a pattern matcher with the plugins. You could have Perl compatible regular expressions. You know, and then what the alert message, basically, what's going to be displayed in your alert. Okay, usually it provides a little bit more information, but certainly this name does appear in the alert. Okay. So here, this is what you know, basically what you see in the file. So Snort rules example. So if you look at the, and this is also what you will get as output, basically. Okay, so when Snort sees something, you will see something that says alert, and then it'll say message detected foo. Okay, so that's what you get on the terminal, nothing else. But it's obviously going to be related to the name of the attack that you selected. So you have to tell me in the lab, yeah, I picked TFN2K, and then here it is, TFN2K shown in the alerts. So you need to provide that screenshot. Here you can see again, just generally, you can look at more examples. Alert TCP, flow is established, and then the content, it contains the word foo. You know, another one is an SMTP exchange mime DOS attack, right? And again, look, this one, the content, right? It includes something like that, plus some specific values, right, that you have available. So this is what you have to, this is pretty much the challenge in your lab, is just kind of finding new families and then figuring out how to create the packets. This is another one, let's call it net exploit, netscape, whatever. And then this is a type, just by looking at the contents here, it looks very much like this is an exploit, and it's right there in the name, right? So you can see that. Again, these are parameters that need to be specified. Sometimes the references, the references are just how this is documented somewhere. So if you want to learn more about the attack, you can look up these documents. Okay, so you can look up these documents, these references, to provide a more clear description of the attack and everything. Okay. So summary, you know, Snort is the de facto standard IDS in the practical security community. You know, it's open source. We can easily study it. It's been around for a long time. It's been downloaded over 3 million times, about 200,000 users. It's lightweight, easy configurable IDS. If you don't want to spend any money, you know, this certainly, you can start here. It's got good performance. It's, you know, again, it's C, C++, libpcap, so it's fast, reliable. It's already a service in your, it's not a code. I want to make that clear. It's not like memcopy where you have to compile it and run it. This is literally downloadable to a Linux machine just with sudo apt-get from a repository. It's a moderately expressive rule language. So, you know, it makes it pretty, I think you've seen, is pretty simple. And then you have basically things that you can add to it, alert interfaces and logging interfaces, databases, GUI tools. And it can help, you know, with intrusion prevention. Okay. So you could build appliances around this, at least for your own research purposes. So some to conclude some elements, to conclude, I guess, intrusion detection systems before we move on to firewalls, elements of intrusion detection. So some of the primary assumptions, system activities are observable, and normal and intrusive activities have distinct evidence, right? So especially in a signature-based environment, you can definitely figure them out. Components of an intrusion detection system, it's got the features in the model. So capture intrusion evidence, that just means capturing, the sniffing part, right? So the sniffing part. And then the model, how do you actually determine if something is an intrusion or not? From an architecture point of view, various components. It's got the audit data processor, again, the sniffer, the knowledge base, which is the signatures, the database. It's going to have some kind of a decision engine, which is, those alerts, think of them as if statements. And then the alarm generation and response, right? So once you get the alerts, or the logs, how do you deal with the alert, which is sometimes this is referred to as alert management, okay? Because it can be very, very challenging. Again, just to summarize, we talked about misuse detection. Basically, we have a pattern matching, a signature, etc., and then we stop the packet. So it's almost like a if statement approach. But it can't detect new attacks, as we said, right? So that's why we also talked about anomaly detection, which is when something is outside the patterns of your data. So for instance, here you can see we have abnormal, and then we have normal profiles. So for CPU usage or processes, et cetera, of devices, you can see normal, right? Normal is the light green. But if you have something that exceeds that, so maybe you can say, well, this is abnormal, but it's still within the range of what we would accept. But obviously, this one looks like it's completely outside the range, possibly. And so something like this could be an anomaly. Okay, so we talked about that. Anything that, doesn't fit what we're used to seeing, the range, basically, or the statistics. If you want to think instead of a range, you want to think in terms of the normal distribution. Okay. However, keep in mind, what's the problem with it? Well, a relatively high false positive rate, right? False positives just means that it thinks it's something is bad, but that's a false assumption. Because first of all, anomalies can just be new normal activities, right? Remember that an anomaly does not mean intrusion. Also, it could be a failure in the system, so it's not necessarily an attack. It's just something happens with a misconfiguration or a hardware failure. And then we talked also, I should say, about AI tools. Obviously, that requires a little bit more work, but this is perfectly in line with intrusion detection systems. Okay, the last part, I'm not going to go through these slides. I just wanted to make a note. This is yet another project topic. Okay, so if you guys wanted to build for your term project, again, you have to have an idea of a network, pretty simple, and then do attacks and defense. But here, the idea would be that, you would write your own idea. So instead of using Snort, you can explore, maybe writing your own ideas with Python, or now what I would recommend is probably just using like built-in libraries. Okay, so and here's just one example, PyNids, right? That's a library that allows you to do more things. So for instance, an interesting project would be if your IDS doesn't just look at packets, but it actually does TCP stream reassembly. So that is to say, it's going to look at a lot of packets, you know, in the network for one specific TCP communication. As you know, we already learned from TCP session hijacking that the key to that, to identifying the session, is that they should have the same IPs, port numbers, and corresponding sequence numbers. Okay. And then basically you can just take a look at libnits or the previous one, PyNits, or I'm sure there's other tools out there. But here, this would involve a little bit of coding, of course, but this would be a nice term project. So if you have an interest in that, just take a look at these slides. There's some examples of the code, to see if you feel it looks accessible, and then consider that as a term project. Okay. All right. So that, I think, this concludes the intrusion detection topic, if I'm not mistaken. Are there any questions before we move on to the next? Okay, so it doesn't sound like there's any questions. So I went over these slides. Okay, so now let's see. All right. So now there's no questions in the chat. All right. So now I've covered that one. And we basically have wrapped up, except for the lab, we've wrapped up the intrusion detection topic. So we should be ready. Just opening up the slides. So let's open up the firewall slides. And this will just be a brief look at firewalls. Oops, sorry. I need to share this. Okay, so you should now be seeing the slides. Let me start the slideshow. I think this is so we are now making that the transition to firewalls. At some point, I have some slides where I just want to point out all the controls that we've sort of looked at so far, or that we're going to look at. Because remember that we've talked about this several times, that security is really a system. Right? It's a system of we use defense in depth, and it's a system of all these different tools. So, as part of defense, we've looked at intrusion detection systems. Now we're going to start looking at firewalls. And we've all heard of firewalls. And so we're just going to go over a lot of details about them. So I'll talk a little bit, how it works, etc. Right now, for today, we're just going to start with some terminology. Okay, and then we have the lab, which, as I said, that lab can be implemented in any device, right? So whether we were using a Cisco firewall, or we're using Linux Iptables, or we're using, whatever it is, it's basically the same things. The only thing that's going to change every time, the logic is always the same, but what's going to change is the syntax. Okay. Nowadays, firewalls are very much GUI focused, but so that that's one of the solutions that companies are selling. We're just going to look at how it works in the terminal, basically, as we do our exercises. All right, so some ideas. So this is basically getting into firewalls. So I don't know why the name here is this. It should just be firewalls. All right, so here's some of the terminology. So first of all, we're going to think about this idea of ingress and egress, okay? Filtering. Firewalls are basically about that. So, you know, one question I always like to ask on the exam is, for instance, what is the difference between firewalls and intrusion detection systems, okay? So that's one thing that hopefully should become obvious as we look at these two topics, right? But in the next exam, you guys should, you know, you'll get a question like that. So think about it, right? So start thinking about it. What's really the difference between IDS and firewalls? As we go along now, let's just think of the terminology. So firewalls have these terms ingress and egress. Ingress just stands for traffic coming into your network, right? So remember again, here it becomes important in a way to once again look at that example, right? We have a firewall, we have a router. This represents the internet, right? So it's very insecure. And then we have domains of trust. So this is the internal network. So this is the internal network. You can think of this as a DMC, a physical DMC. And then this is the outside. Well, the outside is actually technically this. So let's just say this is the web, actually. All right, so the idea is, remember, these are devices with two network interfaces. That's one of the key aspects of this. And they basically perform routing functions, but as they perform routing functions, they have a set of rules, right? That once again, you know, the packets each, but this time around, what's different is in the firewall, every packet needs to go through those rules. Okay, so this needs to be highly efficient. And that's why firewalls can be expensive, right? Because of the hardware itself needs to be pretty fast. Remember that they also do encryption, you know, they do all kinds of things. So, but as we start looking at these terms, ingress and egress, what this means is basically in terms of this network, right? So we have ingress traffic coming into your network. So it's traffic going in that direction, right? And egress is traffic leaving your network. So it might be, you know, your users, so like your, you know, your employees, and they're going out into the internet, right? or outside the network. Okay, so firewalls have rules for incoming traffic and for leaving traffic, and they always follow something like this. So if you look logically speaking, regardless of the syntax, they all kind of have this idea where the rule is something like block all or something in from IP. So the in implies for incoming traffic. So it's almost implying the direction that the traffic is taking, right? The other one might be, and this is dependent also on the interface that you assign this. So usually what's going to happen is, remember, you have two interfaces and you associate rules with the individual interfaces, okay? So a lot of that will depend, you know, once you know the interface, once you know the direction of what you care about, you're going to say either block all in from IP, which implies for incoming traffic, or block all out traffic from IP. Okay, so where this just indicates which IPs, that can be a specific IP or a subnet, etc. And we'll see as we start getting into the lab, we'll see some description of how that works. Okay, so that's the whole point of the labs, right? So we'll implement some of these rules going forward. But for now, we're really just in general terms, generically speaking, we'll be talking a little bit about the the syntax, not syntax, the terminology. Sorry, the terminology. I also have some slides on how these commands work in like a Cisco environment. So we'll also go through those so you can take a look at them. So here, as we continue our discussion of ingress and egress filtering, so here we look at a network, kind of like the one I drew before. The idea is you have the firewall, of course. We have the inside of the network. Remember, that's the most trusted environment. That's where you have your employees. This is the outside, the web, right? So attackers can be out here, whatever. So then you have egress filtering and ingress filtering. So you can see ingress is on this side. It's blocking incoming traffic from one of the set of invalid networks, from one of a set of invalid networks that you don't want to authorize. Egress filtering blocks outgoing traffic that is not, that you just, disregard this, just basically any traffic that you want to block, basically, okay? Ingress filtering here, filter out packets from invalid addresses before entering your network. Egress filtering, filter out packets from invalid addresses before leaving your network. And invalid just means, maybe the word invalid is not the best one. It should be maybe unauthorized, something like that. Okay. Some recommendations. Remember that in the internal network you have private schemes, right? Private address schemes, such as the 10, the 192, etc. So one recommendation could be that you just block anything that has these networks. So we're going to see network address translation in a second. But you can see here that blocking by subnets can sometimes be useful. So let's take a look at NAT actually. So network address translation. This is just, you guys have looked at this before. The idea with this is that you have a device and then you might have, let's say, just two subnets here. This is the firewall and then you have a switch and then you have a switch. So this could be the 10.0.1.0 network, right? And then this could be the 192.168.1.0 network. So the idea with network address translation is that as a packet is leaving this network, the source IP in this network is going to be something like 10.0.1.3, let's say, right? That's going to be the originating IP. But as it crosses the firewall could be configured to perform NAT services. And what that means is basically that the source IP of that packet, think of it as any other packet you created, that source IP now will get replaced by an IP in this subnet. Now, how do you do that? You usually establish what's called a pool of IPs that are reserved for that purpose. So it could be something like from 192.168.1.5 to .30, right? So you have kind of reserved those 30 IPs, and then the IP of the packet as it crosses the network will be replaced by this one. Obviously, when it comes back, right, there's going to be a table in there that can once again replace that IP address with the original 10.0.1. Right, so that's really ultimately what it is, and it's a simple configuration. So NAT is one of the services that firewalls do provide sometimes, translating private addresses to public addresses, for instance. NAT methods, basically they can be static translation, one-to-one, or many-to-one. So static translation, internal IP corresponds to a specific internal IP address. One-to-one NAT, its internal IP corresponds to a single external IP, but changes day to day. All right, so I think that's usually like your ISP kind of does this, I think, usually nowadays. Or actually, let me rephrase that. This is how it used to be, and now it's become a little bit more static, I think, and that's because advertisements, right? So I think honestly, the industry of so if you think about it, if you're think about this, if you're, you might disagree with me, but think about this. If you're AT&T, right, or if you're Verizon, and you want to keep track of people and what they're viewing, that you know what they're searching, so that you can advertise for them better, you kind of give them a fixed IP. And so that way it's kind of this static. So regardless of what your internal IPs are in your network, when you leave to go on the internet, they actually always track you with a static IP. And so I don't know what it is exactly right now, but I know over the years I've noticed this was a common thing, and now it's been a little bit more static. But I may be wrong. And in essence, I think the change has been, although they track you in various other ways. I mean, because there's no legislation in the United States like in Europe that protects your privacy. All right, so, and then there's the many-to-one NAT, also called port address translation, which is basically when large number of private addresses can be translated to a single public IP address, but there's a port number associated with it. Okay, so that's just one of the services that's involved, so I wanted to mention that. Firewalls will provide that. I wouldn't say it's necessarily a security thing. If anything, I just gave the example of privacy. So you might want to take a look at that. Here's just an example of what I just said. So basically hide from inside to outside. So you have the 192.168.1 network right on the inside, and then when you go out to the outside, it gets mapped, static map, from inside 192.1.5 to 128.274.1.5, whatever it is. Okay, so that's all it is. Remember, usually this is a service the firewall can perform easily. ASAs, Meraki's, Cisco, Pixes, whatever. These are services that are kind of standard in one of those devices. So we've talked about this, so static mapping. Okay. ICMP, that's another thing that is important. You know, we've been looking at a lot of examples of this. So remember, the internet, ICMP is the Internet Control Message Protocol. It's used for ping, as you know that, obviously, for troubleshooting and error reporting. But the threat is, of course, recon and floods, right? So we've seen how this can work already, the attack. And so the question is, you know, what do you do with ICMP? Well, as it turns out, again, firewalls can easily drop ICMP packets. So that's usually a standard set of rules. We will take a look at those. It's like their own. They used to have, like in the old Pixes, they used to have like just a command called ICMP. It was really that important, right? Over the years, the providers have just made all rules kind of more consistent. So I think that has been phased out, but generally speaking, you could set a parameter in a firewall to just not allow ping. You know, ping. I mean, you can allow it if you want, but you can by default kind of just drop ping packets if you want. Okay. So let's see. Here's an example of just how firewalls kind of work. One of the terminology again is going to be ACLs, access control lists. We'll think about those as we start moving forward. Basically, you define ACLs on a device like a router. Remember also, I should say, and you know this, of course, that a router, just like a firewall, can have ACLs, right? Really, the difference is that, you know, a firewall might have more services, etc., more powerful sets of rules, but routers also have ACLs. So now let's look at an example of an ACL here. So we have on a router, let's say an access control list for 103. That's kind of like the file. Think of it like, you know, the file is called 103. And then you're going to tie that file to an interface of the device. And then you look at the rule. So the rule is actually you want to permit ICMP from this host any, right? And then you print out some information. So in this case, we can take a look at the network. We can see there's an internal network. So this is the inside. And it's the 126.0.128 network. We have over here, this is, think of this as a firewall, a device, right? And it's got 3 interfaces. So that's also a common thing with these devices. They can have more than 2. So this has 3 interfaces. It's got the inside, which is the internal network, the most trusted, obviously. Then it's got the least trusted, which is this network, the 192. And this is obviously, you know, this connects to the ISP. It's a little bit outside, a little less trusted. And then you have this public server segment. So this might be your web server, which can be accessed from the internet. So remember that the internet is somewhere around here. That's the web. So if a user is coming in, you know, they go through the router, then this is, you know, more of the firewall with more ACLs. But technically speaking, the ACLs would give permission to get to the web server. Okay? And you can see that here, for instance, this rule just says this is tied to this device, most likely to one of these 2 interfaces that is relevant. And so you would say permit ICMP host 126.0.64.10. So this is the .10, right? So you're saying that this from, you know, from any basically. So you can allow any packets going to this machine, you know, they will be accepted basically. Now, we will see later on that firewalls actually have this idea of, what is it? I always forget how this goes. It's implicitly deny, explicitly accept, right? So, which means you implicitly deny everything and then you explicitly accept individual things one at a time. So that concept also in the terminology will become more obvious as we start going over the notes, you know, next week. Next week I'll do, you know, a few more notes. But today, you know, today I'm just kind of going over, as I said, terminology and just giving you like a big picture of some of these ideas. Okay, so that's an example there. Other examples, you know, we can think of traffic that uses different paths for its return than the original path, right? So let's say that this is some internal university network. This is the classic example of the campus, you know, 2 routers. So maybe what this is saying, if the packet goes in this direction, but it, you know, but it returns on that direction, right? So what needs to happen? There needs to be obviously some communication between these 2 devices so that they have updated tables, right? And you can see that there. So, you know, you have the security devices. Now firewalls have been added. So we've added stateful firewalls, and stateful firewall used for outgoing message adds an entry in its state table to enable the return traffic. What if the response comes back on a second path? Given that the other, you know, it would leave in this direction, but then it comes back in that direction. So the solution basically is have firewalls update their state tables so they are synchronized, basically, as you can see. So that's what firewalls are like, right? So it's pretty much they have these, they can have state sometimes where they, like I showed with the NAT, right? They have a little table of mappings, and then if you have this kind of thing, you know, have firewalls update their states. as possible. Other things that we can think about, stopping network flooding, right? So we've talked about denial of service, right? And SYN cookies. Now we're just going to throw the firewall kind of in the mix as well. If you remember, when we did SYN flooding, we attacked the server, and we did the SYN cookies on Linux, which was available. All right. So, but now, you know, since we're talking about the network, we might have, you know, a target device, but the firewall is kind of before it, and then this is the internet, right? So something like that. So if you're going to do a DOS attack, the attacker is over here, and they're, you know, just DOS, DDoS, whatever, right? Now the firewall is kind of in between, so you want to think about, okay, you know, what can the firewall do, stopping a network flooding attack, for instance. So, you know, a basic ACL, drop any traffic destined to the target IP address, right? That's the simplest thing. Now, there's other things that you could try to do also. Inject a route into network so that traffic destined to an IP is routed somewhere else and dropped. Remember that one of the things that ACLs can do is they can take a packet and modify it. So a firewall can easily do that. And so you can change it so that if you've attached to your network, you know, a honeypot, right? So you've attached a honeypot, you know, you can always send the data there. So reroute to a network honeypot where system administrators can examine the traffic. Okay, so that's an example of how firewalls can act as modifiers of packets and just redirect them somewhere else. You could also do the SYN flooding, basically the SYN flooding or the SYN cookie, sorry, mechanism that we talked about here, SYN cookies. You could also implement it in the firewall, right? So literally the firewall is the one that's actually experiencing the DOS and it's doing the SYN cookie. And then that way it never actually gets to the device back here. So that's another. So basically you just put the firewall kind of before the device and it performs the exact same task that we learned about in the lab. So that's another suggestion there. When it comes to e-commerce, this is why we've been talking about kind of that physical idea, so of separating the network into what you can call a DMZ. Remember that this could also be just an interface on the device, but basically this is the internal network. This again is the web, the insecure web, or not a very trusted domain. And then here, when we talk about e-commerce, what are the design techniques to mitigate distributed denial of service attacks on e-commerce? So separate e-commerce users from internal users. So what that is saying is these are the internal users, right? So these are your, this is your finance, engineering, your payroll, etc. And then the e-commerce is kind of placed outside. So whenever you see me draw this DMZ, it's because here is where you would have your e-commerce. So your e-commerce server, your Apache web server. So what's the difference? Really, ultimately, the only difference is that here you have ACLs and here you have ACLs, which are, as I said, access control lists or rules on the firewall, okay? But these are more restrictive. So these are gonna be, that's really ultimately the only difference. These are going to be more restrictive. These ones, for instance, will have port 80 open, whereas port 80 is not going to be open here, okay? Usually on a firewall, all ports are closed, okay? The only thing that's accessible, so keep in mind, what I mean is when you're coming from the outside in originally, right? Obviously, if you initiate from the inside and then come back, that's a different story. But if you're talking about the firewall here and going into the internal network, port 80 would be closed. However, it is open on this one, right? This assumes, of course, not the 3 architecture, but just kind of this physical layout. And this just to illustrate kind of the only difference between both of these are performing routing functions, but you know, so, let's say you know, you have an attacker or you have a customer. Both of them can get through here and get into the e-commerce server, but your internal network is protected. Okay, and that's what sort of what this is saying here in this environment. You also may want to distribute critical systems into multiple data centers to lessen the significance of an attack. So, you know, by definition, an e-commerce solution is a distributed solution with, you know, the database server is a server, the logic server is another server, and so you can really have this distributed out. Obviously, now with the cloud, you know, that's usually handled by cloud services. Here's kind of the same drawing that I just did. So pretty similar idea. This also just talks about separating it. All right, so this is all e-commerce. And then let's see, TCP SYN flooding. This is what I said before. Actually, I was looking for this slide. I knew it was somewhere in here. This is just what I had said before, that you know, protection for SYN flooding, the firewall basically can perform the SYN cookie function, right? So, or it could just perform the actual function. So firewall retains the SYN information until it receives the third part of the handshake, and then forwards all to server. If it does not receive the third part, it never reaches the server. Remember that the handshake has to occur first before data can be exchanged in the process. So the overflow buffer with too many incomplete handshakes only happens in the firewall, you know, instead of in the device. So that's all that is saying. So what is the goal of a firewall then? You know, I've given you some examples of some scenarios, just kind of, again, to motivate. So today's goal is just to motivate, you know, this defense mechanism. We will, of course, have to go into a lot of detail, you know, you know, and that's where the lab is really going to shine. You know, the lab is pretty nice. But the goal of a firewall is at the end of the day, you have a trusted domain and a less trusted domain, right? So usually referred to as the inside, and then, so you have, you know, this is more trusted, and you put the device in here in between that will perform tons of services. So ACLs, firewalls actually, like our ASAs that we have in the lab, they, you know, they're VPNs. They do NAT translation. They can do login. They have IDS rules. They can be run through the terminal and GUI. What else do there should be NAT. So lots of things. So I can't remember all of it now, but they have a lot of services that are provided by these devices. Okay. At the end of the day, they're definitely one of the central defenses for network security. And so we'll spend some time. Obviously, we're going to talk about these topics during the rest of the semester. Application, the proxy firewall, we will talk about this one as part of the lab. There's actually, just like there's Snort, there's something called Squid. And so we will, this is also a Linux service that we can install. That's a proxy firewall. We'll take a look at that one. That is called an application layer. So in the OSI model, you know, regular firewalls have to be really fast, right? And because they have to be really fast, they're usually like level 3, you just IP kind of thing, or TCP. And they don't go as far as the application. But there's a few out there that are application layer level, and they're called proxy firewalls. So we'll see how these work. So no need to get into that right now, but just be aware. It's basically firewall software, and it runs in the application space. So the firewall. So there's got to be some configuration that happens there. So the example we'll do is like blocking Facebook specifically, right? So we'll put in rules so that we can block certain websites. So it's a more specific type of firewall. And then the ones that we are mostly familiar with are the packet filters. And this is, you know, better described in the PDFs and the documents that we'll start reading soon for the lab. So don't worry about it. Again, today, just motivating. So operates at layer 3, you know, in the router of the firewall, has access to layer 3 headers and layer 4 headers. So basically, what are you talking about? It's what we did all semester so far, right? You know, we're blocking based on source and destination address, ports, and protocols. But it does not reconstruct layer 4 payload. You know, it doesn't have that syntax rule engine that it can look at the payloads. So it cannot do reliable layer 4 analysis or higher content. Remember, again, why? What's, you know, you would think this is important, right? But why? Because remember, a firewall, packets definitely need to go through it. And so remember the performance. You know, if performance wasn't an issue, believe me, they would check everything in the packet, right? But that would be pretty slow. And so that's a limit currently of just the hardware. And, you know, the fact that you want to, you know, think of a network, you want, you know, how fast you need it to be. Stateful packets, these are the ones where you keep track of information. We'll take a look at those later in the semester. So we'll take a look at those. Access control list, I've already said, so you'll hear me every now and then in this lab, and you'll see it in the PDF itself of the lab. It'll talk about ACLs. These are access control lists. Remember that access control is one of the, you know, key things in security. It's used to define traffic streams, right? So keyword there, streams. I like to think of them as pipes and how you're connecting pipes, and the packets are flowing through these pipes, but we'll take a look at them. Usually you define a file, then you need to bind the ACLs to an interface and an action. Okay, so that we'll talk a little bit more about that. But, you know, that's why we did sniffing and spoofing, right? So you already know that at the end of the day, we're just looking at the same fields. We're looking at the source address, destination address, the protocols, source port, destination port. And a lot of the labs will revolve around that. So, you know, how do you block this, block that, etc. Okay. All right, and that concludes the firewalls. Again, this was more of just motivation, kind of to get us to start thinking about firewalls. And then now, the last thing I will do, let me just check the slides. So I covered this one. So that's, you know, the firewall motivation slides, that's done. I have to get into like a more technical one. And then there's some slides that have to do with just kind of talking about all the tools, but I'll do that one another day. So the last thing I want to point out is the PDFs. So I know there's some of you that have already finished the assignments. And so let's just, for those of you that on Thursday will probably need to start the Firewall Lab. So let me just point out where this is. All right, so as you know, we've started to talk about firewalls now. The module, our current module is this one, Seed Firewalls. You can take a click through that. And then you can see I've loaded 3 documents. They're basically the same one. It's just, you know, the evolution of it. But there's always new problems. So start reading through them, okay? I suggest probably start with the oldest one and then read the 2016 and the 2021. And then, as I said, I will start creating links for the different problems because it's a really large lab. Although it's just one document, some of the things are really involved. But just to kind of give you an idea, you know, we can take a look at it. Basically, we will do, you know, one simple one. I still have to cover IP tables, so we'll do that in another lecture. But basically, you know, just adding some rules, right, as you might imagine. So the ACLs. We'll take a look at how this can be done with IP tables and also with UFW. Another problem will have to do with dealing with the Linux kernel module, or sorry, the loadable kernel module. And this is a way that you can write code. So we're going to write for this problem a little bit of code of just so that we can see how a firewall actually works in the code, and then we're going to link it to the kernel of the Linux operating system. And the reason for that is that it'll be faster than if we were just running it as regular C. And then we'll take a look at some ideas like evading a firewall. So how could you actually bypass, you know, a firewall, right? So we'll take a look at some ideas there. You can see, I'll explain this later, of course. And then finally, this one, yeah, this one is Proxy Firewall, so which is what I was talking about. So we'll take a look at how a proxy firewall works. You know, that will be another set of problems. Disregard this, we're not going to use Perl. And then, yeah, so this, you know, we'll go over this, but for those of you that have already finished the other labs, just, you know, go ahead and start reading through this document. Once you finish that document, I do recommend, you know, just grab the next one, 2016 here. As you'll see, there's some similarities, but there will be a few new things. Also, I should point out, you should be reading chapter 17 of your book, which goes along with this. You can see here, this one is, it's got more information about the rules of IP tables. So we'll be definitely in this one. Whereas before it was UFW, this one is actually IP tables. I spend a lot of time on this too in the semester, so I'll show you guys how this works. Again, the Linux kernel module, this one is probably the exact same thing. This one with egress has a few other problems, so we'll read through these. It's got a nicer diagram now. Commands are pretty much the same, hasn't changed. I'll explain all of this later. And then evading, so that was evading. So you can see this one is, it's got more, a little bit more. So we'll take a look at that. And then just, you know, it's got more explanations on the Linux kernel module, on the C part. So again, some of these topics I will explain in the next lecture, but for those of you that are done, just start reading through it. I'm sure you can solve some of it on your own. And then finally, we just got this one, right? So it just came out in January of this year. So I'm still looking at it, but I believe it's pretty much, we disregard everything with Docker. So we're just going to use the VMware. It's got the Linux kernel module again. Yeah, so Linux kernel module. So read through it. Again, this one's got Linux kernel module here. It's just a better explanation every time of the problems. So this one's got a lot more detail, as you can see. IP tables, again, as I said, that's really important. So you can see it's got more explanations of IP tables, and I always do a lecture on IP tables. IP tables is literally the Linux firewall. Okay, so sometimes you see something called UFW, but UFW is just an interface for IP tables. So if you really want to understand like the inner workings of it, you really have to look at IP tables. And then you can see here it's got more examples of how to use IP tables. So we'll take a look at this, and then I'll create a set of problems. I usually what I do is I just create like 5 to 10 problems that I want you to solve. So I have to think about that. But this is a really good read. It shows you basically the syntax of it, right? So how do you write the syntax for various scenarios? Now this is an interesting one because this is new. It's connection tracking and stateful firewalls. So we'll certainly look at that as well. Stateful firewalls, that's a new thing in this lab. Limiting network traffic, you can see that. Load balancing, these are new problems. So we'll take a look at those. Should make it more fun. All right, so again, you know, no, I'm not assigning this yet, but just start reading through these documents. Okay, there's certainly a lot of reading there for you. Plus, also start reading through chapter 17. This Thursday, finish up. I want to see you guys finish up. So I'm going to give you that last lab to finish up IDS and TCP/IP's session hijacking, and then next week I'll jump into the next lecture. It'll be a lot more detail about all of these problems, okay? So that we can start working through them. All right, and that's it. So it's time. It's the end of class for today. So I'm going to stop the recording now.